All right, so a common thought of why a bit of fluid would increase velocity as the area gets narrowed. A common thought is that it kind of gets compressed in there, and for it to get compressed, it has to go faster. But it's actually not because of compression, it's because of conservation of volume. So we need to conserve the volume. I'm just going to write here, conservation of volume. And because of conservation of volume, I need the same volume of fluid here as I would have coming out. So if this is like volume V1, and it's like a hockey puck kind of shape of fluid that I've pulled out of there, okay? Well, now that has to move along the tube, and it has to move along, but that same amount of volume has to now fit in this area that's really, really small. And volume is cross-sectional area times length, right? That would be sort of the volume of a hockey puck. And this is like a hockey puck, but it's got beveled edges because it happens to be a diffuser, right? But basically it's the cross-sectional area times the length. Here, the cross-sectional area is two different areas. But anyway, you can calculate that volume. But if I were to take exactly this fluid and I moved it along this diffuser and I need to fit it down here, then it's going to take up more length, isn't it? Because it's skinnier. So it's like now it's at the bottom of the cup, so it's going to take up a higher length, right? But that has to move out, and it has to move out at the same volume flow rate. Volumetric flow rate means like the kilograms of this hockey puck per meters cube that it is flowing through has to be the same. So it's going to go from this hockey puck to basically this hockey puck shape. And in order for that to move through with that smaller area, then this area went down, then this velocity must increase for it to fit through there. So, and we remember that because of our continuity equation that relates our area and our velocity and our flow rate. So when we look at our continuity equation with our area, our velocity, and our flow rate, we recognize that the flow coming in has to equal the flow coming out. And the flow coming in is area times velocity, Q equals AV. And that is one of our basic equations. Q1 equals A1V1, and Q2 equals A2V2. And if we put the units in there, we'll see that Q is going to be that cross-sectional area times that velocity. Remember, our velocity is a distance over time. So we're going to get meters cubed over time. So we're going to get a meters cubed over time for that flow rate. But that flow rate doesn't change. So this one will have a lower velocity if the area is bigger. This one will have a higher velocity if the area is bigger. You have density on both sides, so density crosses out. So this little fancy shaped row here is our density, so that just crosses out. So as area decreases, then of course that velocity is going to increase. What does that do for our actual energy equation? What this means in our energy equation is that when we have a mass flow, then our mass flow can be represented by area times the velocity of that flow, instead of being represented by m dot. Let me just write it on the screen. Instead of being represented by m dot times h plus EK plus EP. So now you have an opportunity to do mass flow as rho AV if you have some velocities and areas in the problem, instead of using kinetic energy, potential energy, and enthalpy. So that's how this relates to the first law, energy balance.